let me introduce you to Diogo Castro. He's going to talk about federated collaborative workflows for Jupyter. Thank you.
Thank you. Good afternoon. My name is Diogo, and I would like to present the work that we've been doing in a project called CS3 Mesh for EOSC. And I will explain a bit what it is, what is the idea behind this federated collaborative workflows for Jupyter that I mentioned. Just a brief note on the place that I work. I work at CERN. CERN is a physics research laboratory. It's actually very close. It's just 3 hours away from where we are. It sits in the border between France and Switzerland. And you might have heard about it because we run the LHC, or Large Hadron Collider, which is considered one of the most advanced machines, let's say, ever built by humankind, and it's a very important research tool for physics. You might know it as well because it was at CERN that Sir Tim Berners-Lee invented the World Wide Web. And given that Jupyter is a web app, I think we are all thankful for this invention. And this actually is not my first time presenting at JupyterCon. I've been as well in the 2018 edition. So if you happen to be curious of what we do at CERN, how our researchers do their analysis, or how Swan, our Jupyter service, was built, I invite you to have a look at this presentation as well, hopefully after this presentation finishes and not during. But today I will just do a very brief introduction and summary about Swan and focus on two particular areas. I don't want to take a lot of time on this. Basically, as I already mentioned, Swan is our Jupyter service. It was built on top and integrated with all the infrastructure and services that we run at CERN. And in particular, there are two different things that we did that distinguish Swan from other Jupyter deployments, which are the way that we distribute software and how we give and make them available, the software packages to the users, and also the storage integration that we did. And starting with the storage, we at CERN, we run a service that we call CERNbox. It's our sync and share service. You can think of it as a bit like Dropbox or OneDrive. And CERNbox happens to be the home directory of our users, which means that every time that they start a session, they will give access to all of their files. They will be given access to all of the data that they need from the different experiments that run at CERN as well. And so you can see that we have this model of even if your session gets killed and you have to start a new one, you have this persisted storage that is always available. And at the same time, then Swan becomes an entry point, like many others, into the CERNbox ecosystem. For example, we have some users that use the sync lines that you can install in your laptop and create workflows around it. They might be doing some work with their preferred IDE in their laptop and immediately go into the cloud and run whatever script they were developing. A very important aspect of this integration is that whatever endpoint or entry point that you choose to enter in the storage, you always have the same view, whether it's from the Swan web interface, from the CERNbox web, via Fuse-mounted client in Linux, the sync lines, you always have access to the same files in the same view. And the same happens, for example, if I share something with another user, whatever method they decide to use to access the data, they will have the same view. Another aspect that I would like to focus on is are the integrations that we did in Swan. As you can imagine, at CERN we have a bunch of external computational services that we run. They target different use cases. And our approach was basically to make Swan to act as a client, as opposed to, for example, starting a kernel directly in these resources, because this allows users to immediately start the session, so they don't need to wait for some quota to allow them to enter in these systems, but also to do single-node analysis, easy to iterate, and then as soon as they need to have the full data and something a bit more heavy, computationally speaking, they can go and distribute their workflow. And as I already mentioned before, again, storage plays a very important role in here because it's thanks to the fact that Sandbox is available from any of these services that our users can switch between all of them, submit data to any of these services, and they will have, again, access to all of the data that they need. It happens that Swan or Jupyter in general is not currently the main method to do analysis in our community, let's say. But I can say as well that there's a major upgrade to the LHC coming. This upgrade will bring a lot more data, and as well, it's also required a lot more computing power to analyze this data. And so the physics community basically decided to start investigating how to integrate all of these services, the ones that I also saw in the previous slide, and to provide basically a cohesive and an easy-to-use system to the users. And so they call this the creation of an analysis facility. And just so that you know, so this is not only at CERN, this is all the physics community all around the world. They tend to be, we are a community, we are all part of what we call the WLCG, or the Worldwide LHC Computing Grid. So this is an effort that is not only happening at CERN. Even though I mentioned that Jupyter is not the main method for doing analysis nowadays, this has been changing and more users are picking it and starting using it. We have an average of around 300 concurrent users per day. We observed a sum of something like 3,000 unique users per year, so that you have some idea of the numbers that we're talking about in terms of storage. We're talking about 3 billion files and 20 petabytes of petabytes of data in Sandbox. This excludes all the scientific data that is stored in a separate instance, because if we start talking about that, it's not 20 petabytes, it's more like almost 800. So you can see that it's less, but still very considerable, the amount of data that our users keep in this system. But either way, all of this data is available from Swan, both cases. What I'm trying to pass as a message from these slides is that this discussion is ongoing, this discussion about these analysis facilities, and so we need to create a new system, and what we are observing is that this trend of more users wanting to use Jupyter is manifesting. So one of the requirements that we're seeing is that Jupyter, and in particular Jupyter Lab, might become the main choice when it comes to do this kind of analysis, and the main choice as an entry point to the analysis facility system. But there are other requirements, like, for example, the ability to perform fast research iterations on large data sets, the ability to convert interactive to batch schedulable workloads. I guess this is also a problem that other people in this community are trying to solve. Ability to scale outside of the facility on occasion. So basically, there are some occasions when the computational needs a lot of resources, and we happen to have them in the outside, in some cloud outside of our data center, and we might need to use that. The ability to reproducibly instantiate desired software stacks. This is actually something that we already do in Swan, so if you want to know how we give access to our users to the software packages, I invite you again to have a look at my previous presentation at JupyterCon. Then you'll have an idea of the systems that we use for that. And lastly, the ability to collaborate in a multi-organizational team on a single resource. So all of our experiments, they span the world. They do not, these users that work on these experiments, okay, they have the detector at CERN, but they are in universities in the US or in any other country. So they have their own resources, they do their own analysis, and how can you do a collaborative analysis if some are in a different infrastructure than the one that we have at CERN, for example? This is a major problem, and actually it's not a new problem. To the fact that 3 years ago, we were creating a project called CS3 Mesh for EOSC, precisely to address some of these challenges. But before, let me just bring you up to date to the world of EFSS systems. I don't know if you are aware of what is there. EFSS stands for Enterprise File Sync and Share. You might know probably the commercial cloud providers like OneDrive, Google Drive, and Dropbox. But at the same time, there are a vibrant community of open source and self-deployable alternatives, like, for example, ownCloud, Nextcloud, Cfile, and PyDio. And we, in Europe, we tend to deploy a lot of these services. We brand them, and we expose them to our users, as you can see here in the lower part of the slide. For example, Cernbox is a very special deployment of ownCloud. So you can see that we have a very strong collaboration with these software companies to the point that we are reuniting every year to discuss how the state of this community is going. We usually call this conference the CS3 conference, which led to the creation of the CS3 community, which also led to the creation of the CS3 mesh project. So you can see not very creative in the naming, but at least it keeps some branding, let's say. And we're talking about sites that span the globe. Again, they have their own EFSS systems. It's relatively large. We are talking about, for example, services that reach 400,000 users. Besides the basic sync and share, these also provide access to rich application layer. So a lot of applications, of course, Jupyter is one of these examples. These platforms allow users to do sync and share, to do some kind of collaboration within the site. But the problem is that they remain isolated from each other. We didn't have any standard API, so the services could not talk to each other. The different applications have different APIs. It was really hard to collaborate across sites, and we would state a suboptimal knowledge transfer was happening because of this limitation. And this is precisely why we created this project to begin with. The project is almost ending, but since we built the foundation of this project on top of these large communities, we expect the benefits and the work that we've done to continue, and we expect to continue working in developing and updating these systems. The main objectives were delivering a global collaboration service. I will talk about that in a bit. Providing an interoperable platform. So basically, we don't want to reinvent the wheel. So most of our sites deploy similar kinds of applications. So if we can find a way to deploy them in a similar fashion, even if our storage technology is different, this is a very nice goal to have. And of course, leveraging the potential of the CS3 community that is always open to expanding with new members. Again, Jupyter is one of the main applications in this ecosystem. These are the partners of this project. They are mostly European. What is important to know is that we're no longer talking just about physics partners. CERN here is the only one dedicated to physics. The other ones are universities or laboratories that cover other sciences and areas. They even target different ages. We have an example in Poland where a partner is deploying Jupyter for secondary schools. So you can see we cover a very large environment of users. And the main product or the main outcome of this project is the science mesh, which is a decentralized mesh of these EFSS nodes that I mentioned. It's a trusted federation of nodes, and basically it provides this environment that our researchers need to, so that they can collaborate across different nodes. And I mentioned here that we tend to have access to the same user experience and kind of features as if you were local users, because here the example is I share something with another user that lives in that works in a different node. They might not even have the same app ecosystem, but then given that I share something with him, they will be able to use an application on my service and collaborate with me as if they were or if this user was a local user. Finally, of course, we also have a portfolio of apps that can take advantage of all of this, because if we don't have apps, this would not be usable for the users. So basically, how does this work? We start with this foundation of storage that I kept saying that this is a very strong foundation to share across services, these EFSS systems that I mentioned. On top, we have a layer that already existed in Europe for this kind of federation and access control, but we evolved it further. What we really spent time working on was in creating what we call here a component that we call interoperability platform, or IOP for short, which basically is the component that can talk to the FSS system, to the storage, the component that can talk to the mesh, but also the system to which the applications can talk to. And you can imagine, for example, Jupyter being one of these applications. And since it doesn't support it natively, what we can do is we create a plugin that can talk to this IOP and then be able to talk to the mesh and to EFSS services. And this is what I'll be talking in a bit. But just before that, so that you have a bit of an idea of why we use Jupyter in this project, we have many use cases, but the two bigger ones are use cases related to physics, so the CERN use cases, so anything related to high energy physics analysis, collaborative analysis, it's very important for us as well. You might be interested to know that, for example, people that control the LHC are using Jupyter to know how the system is working and to debug issues with the machine itself. Education and outreach is also very important to us. Then on the other side, you have the Earth observation use cases. This is from our partner JRC. So basically, they have access to data from the Copernicus Earth observation constellation, and they are creating, using Voila, amazing dashboards that are used by decision makers to take decisions on, I don't know, resources, how they are being utilized in Europe and things like this. I can remember one dashboard where they were monitoring the fires during the fire season in the summer across Europe, and this had an amazing detail. It was a very cool usage of creating dashboards with Voila. But one important message here is that, okay, CERN is in the middle of these two communities, and it's in the intersection of both, but the things that we're developing span not only the physics community, but as I mentioned, everyone in different sciences that can be part of this science mesh community. So we are bridging a bit the gap and functionalities between these two different communities. But let's go and see a bit more about this plugin I keep mentioning. But before, sorry, another detour, because we were looking at the current collaboration model of Jupyter Lab, or Jupyter in general. And basically, when this project started, there was a big issue if you use the distributed file systems, which is our case. This could lead, so it was not possible to open the same notebook in parallel, so this could lead to conflicts, could lead to data loss. This was a real issue that our users were feeling. Nowadays, with this new mode that we've seen presented here as well, this collaborative mode, this no longer happens. It really looks amazing, and it was a wonderful job that it was done. But this coming from someone that doesn't know in detail how this works, so sorry if I'm making a mistake, but it looks like the optimal usage at least requires sharing the same Jupyter server and kernel. But we see some problems with this approach. For example, since you have a distributed file system like, or if you have a distributed file system like we do, you might not be accessing Jupyter with the same Jupyter instance, let's say. At the same time, I tried this new model, and it kind of worked. You didn't create conflicts, but the problem was that sometimes my notebook was being updated, and I had no clue that someone else was on the other side editing, because the changes that appeared, and if the notebook is long enough, it might not even see that is happening, and this might break the notebook itself. At the same time, as I mentioned, we are talking about collaborations in our experiments that have so many people that it might be hard to do this kind of coordination on how to do concurrent editing like is what is being proposed. And the reason why we don't want to run in the same server and kernel is we consider this to be a bit risky. Because as you saw, at least in Swan and the kind of services that we offer with Jupyter, you have access to so many things and you have so much power in your account that if you want someone else to impersonate you, this opens the door to some problems that we are not very happy to expose our users to. And at the same time, the last point is that we are not really aware, we might be mistaken, but we are not really aware of any use case that would, at least in our community, of course, that would benefit truly from true concurrent editing. Some cases I can see the point in having it, of course, but it's not the full thing that our users are needing. So that's why we propose a complementary model that is a bit more suited for large-scale distributed environments, which is done in this plugin that I mentioned. So this plugin, finally, it's a generic Jupyter Lab extension. We also have some implementations for the backend to replace the contents manager. It should be platform and infrastructure independent. And what it does is that it's able to talk to this IOP that I mentioned before. So if you have your own EFSS system and they have this IOP or interoperability layer on top, we can deploy Jupyter exactly in the same way, even if you are using a different storage service than myself. This is a bit the objective, to simplify how we deploy Jupyter. And of course, not only that, then you also get the bonus of being able to access the mesh. We also are bringing the full experience that you have inside the EFS system into this plugin. So basically, you have access to your files, of course, to the versions, to the shares. You can share with other people. So basically, what you can do inside an EFSS system, you can also do from Jupyter, which our users also think it's useful because they don't have to keep switching back and forth between apps. But last, what we also bring is what we call parallel access to notebooks. We see this a bit as an alternative to concurrent editing, where we basically keep some independence of the environment. What does it mean, having a parallel access? It's not that complicated, actually. We basically use locks to prevent users from editing at the same time. One advantage of this is that you always know who is the user, the other user that is editing the notebook, because you need to know who is the owner of this lock. So, of course, you know who is editing the notebook and is preventing him from access. And another advantage of this is that basically, if you're not entering and accessing these files through Jupyter and you are accessing through a different place, you no longer create conflicts, because even if you don't have support for this kind of locks, the point is that the storage layer can enforce it, so you are not able to override someone else's changes, which is very important for us to ensure that we don't lose data. I say this is a different approach. I mean, basically the usage is that you open a notebook, you are the first one, so you lock it. If you are the second or subsequent user, you are given two options. You can open it in read-only mode, or you can create a copy. It's different, yes, but I would say that it's actually complementary to this concurrent editing model. So I don't see a reason to not have both and to target different use cases with these two approaches. There are still some work to be done on this plugin that we're still doing. And the point is that, okay, yeah, you as a user that cannot access the notebook and that had to create a copy, you are working in a separate and a split copy of the original. But then what? Of course, you might want to merge these changes. So this is something that we are trying to do to help users to get there. And it was mentioned a couple of times today already, this NB time, and we are using this. Of course, what is also missing that we still need to finish some tests is to enable the real access to the mesh, because we've done this, but we still need to do some tests to be able to share across different nodes. And just a note in here, I mentioned before that one approach that applications can do is that, okay, I share with someone, that person can open the same app inside my node, but given that Jupyter gives access to the resources, this is a bit hard for our security team to accept. So at least for now, we're just talking about remote access to the files. Just before I conclude, this is almost the last slide. I would just like to point out some other work that we're doing in our project. There's this library for Voila to create very powerful and multi-layer dashboards. It's really interesting. This is what JRC uses. And lastly, some work as well in creating services for deploying Voila. I've seen a couple of them today being presented. So since we are starting this, maybe it's a good thing that we will talk to these people instead of doing the service ourselves. And lastly, we're also testing different ways to integrate this storage in a way that it becomes accessible to the kernels as well. In our case at Swan, at CERN, this has been solved since the beginning, but this is not the case everywhere. So of course, we are testing and documenting what are the options for other people to deploy. That's all from me. If you are interested in joining the mesh or to know more about, please let us know. We are always open to new sites or nodes. Thank you.
Thank you. OK, folks, we have a few minutes for a few questions. Any questions? Yeah.
Science Mesh was a deployment of ownCloud, is my understanding. And I'm curious to understand how much extra magic on top of ownCloud has been added in that process. And I don't know the details to further elaborate on the question, but something about the distinction about ownCloud and service mesh.
Okay, so just a clarification. So Science Mesh, we had already a bunch of nodes across Europe that deployed ownCloud, Nextcloud, etc. And we created the mesh as a way to interface between all of these, to connect them. And this has been done by, OK, there were some changes in the core of the product, but there is some app that you can install, and this makes you register your service into the mesh. It's not available in the latest OSIS, the new version, but actually CERNbox is now built on top of that, so we are working to bring it into it as well. This is part of the work still missing.
Yeah. Any other questions? OK, I have one. About the lock, or the locking mechanisms that you were talking about, can you give a little bit more of details about that? It's an interesting problem. I faced that problem in the past as well. And if I understood correctly, you have different applications that can be interacting with this, I mean, on the back end. And you need to implement an agnostic way to do the locking. So if you have just a summary of how that is implemented, that might be helpful.
So different storage backends might implement it differently. That's why this is also part of these CS3 APIs that I mentioned. So this IOP layer basically pushes back to the storage to implement this. In our case, we have a technology developed at CERN that we call EOS, and so we really lock it there. It comes from Swan, and it goes directly to the storage and gets locked there. That's why, for example, if you go from the sync client and you try to overwrite some file that I'm editing, the sync client will not be able to do it because EOS will say, no, this file is locked. And actually, this is also useful because, for example, if if you are at Swan, you have different servers, yes, but even if you had the same server, if you wanted to start going to the mesh, you might have a different Jupyter server running in some other node and accessing the same file. So you really need to have some way of coordinating these two.
That makes sense. Thank you. Yeah, one more, the last one.
Thank you very much for this talk. But I'm wondering about, because I suppose this will be part of the skeleton of EOSC,
Yeah.
if I understand. And well, we have other ways to authorization and identification more that EduGain services. It will be compatible also, for example, I think in AAC. Services, especially in life science, because we are using this. And,
exactly. So I don't know in very detail, but always, again, these are blocks. So when we mention this as being a block, is that you should be able to replace with something else. We might need to do some work in doing some kind of API layer that is common, but sorry, at this moment I cannot tell you in detail about it, but I would say this is the expectation, yes.
Okay. Thank you, Diogo.